In Chapter 6, we were introduced to a unit that we call the mole in chemistry. The mole is the chemist's dozen, and we know that for every 1 mole, there is 6.022 times 10 to the 23rd particles. And these particles can be atoms for individual elements or molecules for compounds, right? And this is just really a way for us to measure atoms, because atoms, this is a huge number. This is Avogadro's number. So it'd be really hard for us to express in these terms on such large scale. So we use this mole. And this is similar to saying 1 dozen is equal to 12 things. Similar process, except the chemist's dozen is much, much bigger than 12. So let's see if we are given that we have 3.45 moles of helium, and we want to know the number of helium atoms exactly. How do we go about this conversion? We use dimensional analysis like we learned in Chapter 2, and we always write what we're given first. So we have 3.5 moles of helium, right? Now we know that since moles is on the top, moles is going to go on the bottom. So for every 1 mole of helium, we know there's going to be 6.022 times 10 to the 3rd helium atoms. So it's a straightforward calculation in which our moles cancel out and we are left with helium atoms, which is our desired unit. And so when we plug this in, we end up with 2.1 times 10 to the 24th helium atoms. You can see that's a very big number to deal with, and that is why we use, it's much easier to say 3.5 moles than to say, okay, we have 2.1 times 10 to the 24th helium atoms. Okay, let's do another example. If we have a silver ring that contains 1.1 times 10 to the 22 silver atoms, how many moles of silver are there in the ring? So we're working the other way around. Again, we always start with what we're given in dimensional analysis. So that's 1.1 times 10 to the 22nd, this time silver atoms. And since we have the silver atoms on the top, we're going to put atoms on the bottom and the desired unit of moles. And we know for every 1 mole, there's 6.22 times 10 to the 23rd atoms of silver for every 1 mole of silver, right? So our atoms cancel out and we're left with moles of silver. Now I want you to notice one thing, that no matter what element that we're working with, there will always be 6.022 times 10 to the 23rd atoms of that element per 1 mole. There's no variation in that. Just like if you have a dozen of donuts or a dozen of bulldozers or a dozen of chairs, a dozen is a dozen. It will always have 12, no matter what your object is that you're measuring, or in this case, no matter what your element is. So you end up with 1.8 times 10 to the negative 2 moles of silver. Okay, go ahead and give this a try. How many gold atoms are in a pure gold ring containing 8.83 times 10 to the negative 2 moles of gold? So we always want to write with what we are given. And since moles is on the top, moles is going to go on the bottom. And we want to know the gold, how many gold atoms. So atoms on the top. Okay. So we know for every 1 mole, there is 6.022 times 10 to the 23rd atoms. Our moles cancel and we're left with atoms. And we get 5.32 times 10 to the 22nd atoms of gold. And another way to just make sure that you got the correct answer is just think about the units. This is a very large number, right? But it seems to make sense because we're talking in terms of atoms here, and atoms are very small. If you got 5.3 times 10 to the 22nd moles, maybe you would want to reconsider your math, make sure that you plugged in the correct numbers because that is a big number for moles. Okay. Now we're going to talk about how we can convert moles to grams or grams to moles. And the reason why we do that is because we don't have an instrument in the lab that measures in moles or number of particles. We have the mass scale that measures in mass, which is given to us in grams. So if we have 0.58 grams of pure carbon, how many moles of that? Well, how we figure that out is by using the molar mass. Because remember, the molar mass for carbon is 12.01 grams per mole. So look at this. This is equating grams to moles. So for every 1 mole of carbon, we have 12.01 grams. And since grams here is on the top, grams of carbon is going to go on the bottom, and moles of carbon is going to go on the top. And for every 1 mole, we have 12.0 grams of carbon. The grams of carbon cancel out, and we're left with moles. And so you end up with 4.8 times 10 to the negative 2 moles of carbon. If we wanted to go the other way around and calculate the number of grams of sulfur in 2.78 moles of sulfur, we would go about the same process, and we always start with what we're given, 2.78 moles of sulfur. And now we look up the molar mass for sulfur, not carbon, because sulfur has a molar mass of 32.07 grams per mole. Okay, and so this is similar to saying, okay, when we have Avogadro's number in 1 mole, we have 6.022 times 10 to the 23rd particles in every 1 mole. That's like saying 12 units or 12 objects per dozen. Okay, and no matter what object you have, like we said, whether it's a bulldozer or it's donuts, it's 12 objects, period, right? But when we are equating the mass here, which is going to weigh more per dozen? A dozen of donuts or a dozen of bulldozers? Yeah, they're both 12, but they're each going to weigh differently. And so that's why when we equate grams mass to moles, we use the molar mass, and that's unique for every element. Okay, so here, since we have moles is on the top, we're going to put moles of sulfur on the bottom and grams on the top. And for every 1 mole of sulfur, we have 32.07 grams. So our moles cancel out, and we're left with grams of sulfur. And this gives us 89.2 grams of sulfur. And again, this number makes sense. To have that many grams of something makes sense. Okay, go ahead and give this a try. Calculate the number of moles of sulfur and 57.8 grams of sulfur. Again, we always start with what we're given. So we have 57.8 grams of sulfur, and we're going to use the molar mass of sulfur as a conversion factor, which is 32.07 grams per mole, right? So now, since grams is on the top, grams is going to go on the bottom, and moles is on the top. And we know for every 1 mole of sulfur, there is 32.07 grams of sulfur. Our grams cancel out, we're left with moles, and we get about 1.80 moles of sulfur, which is a number that makes sense for moles. Okay, now we're going to take it a step further, and we want to know the number of carbon atoms in 0.58 grams of diamond. Not just the number of moles, but we want to know the number of atoms. So we always start with what we're given. In this case, we are given 0.58 grams of carbon, which is diamond. Now, we don't have a direct conversion factor that will take us from grams to number of atoms, right? We have something that a conversion factor that would take us from grams to moles, which is our molar mass, because our molar mass is 12.01 grams per mole, right? Just like in our nail analogy, we have for every 0.300 pounds of nails, we have 3 dozen, let's say. Okay, we don't have. We're not saying that we have 0.300 pounds of nails. We have 30 nails. We're converting first from mass to dozen, and then we convert the dozen into number of nails. And same thing here. We have the grams that we must convert to moles, which is our chemist dozen, and then we can go to number of particles or atoms. So let's, with that in mind, we're going to use the molar mass first to take us from grams to moles. So we have 12.0 grams of carbon for every 1 mole of carbon, or let's say 1 chemist dozen of carbon. Now we don't want to stop there because we want to know how many atoms. Okay, now this is really easy because we know for every 1 mole of carbon, we have Avogadro's number of atoms of carbon. So you see the grams cancel out and the moles cancel out, and we're left with atoms just like we were asked. And this gives us 2.9 times 10 to the 22nd carbon atoms. And this makes sense because it's such a big number, and atoms are very small, so we would expect to have such a big number. Now, if we want to calculate the mass of 1.23 times 10 to the 24th helium atoms, we would go about the same process, but we would start with our given. So 1.23 times 10 to the 24th helium atoms. Again, we don't have a direct conversion factor that will take us from the number of atoms to the mass, but we do have a conversion factor that will take us from the number of atoms to how many moles, or how many chemist dozen of atoms, and then we can take that to figure out the mass. So here we know there's always 6.22 times 10 to the 23rd atoms of helium for every 1 mole of helium. Okay, so now we don't want to stop at moles. We got to take it one more step to figure out the grams. And how do we equate moles in grams? We use the molar mass, because don't forget, your molar mass is in grams per mole. It's a conversion factor. So since moles is on the top, we're going to put moles on the bottom, and we know for every 1 mole of helium there is 4.00 grams, okay, of helium. So now our helium atoms cancel out, our moles cancel out, and we're left with grams, which is the mass that we were asked for. This gives us 8.17 grams of helium. And that's a number that makes sense. Okay, go ahead and give this a try now. How many aluminum atoms are in an aluminum can with a mass of 16.2 grams? So we always start with what we're given. Now, we want to go from grams to the number of atoms, but we don't have a direct conversion factor between grams and number of atoms. We have a conversion factor from grams to moles, and then we can go from moles to number of atoms. So it's going to be a two-step process, right? So we have, we use our molar mass of aluminum, in this case, to go from grams to moles. And since grams is on the top, we're going to put grams on the bottom. And we know that there's 26.98 grams of aluminum for every 1 mole of aluminum. And of course, we found that on the periodic table. And then we go from moles to number of atoms. And we know for every 1 mole of aluminum, there's 6.022 times 10 to the 23rd atoms of aluminum. The grams cancel out, the moles cancel out, and we're left with atoms just like we were asked. And when we plug this in, we end up with 3.62 times 10 to the 23rd atoms of aluminum, which is a reasonable number considering that we have such a small number of atoms. So atoms are so small that we would expect such a large number for the number of atoms.